This afternoon we have about 7 talks remaining, and they are going to dive deep into the technical architecture of everything from hierarchical mempools to heterogeneous Braca broadcast. So I hope you will stay tuned for all of them and see what suits your fancy. We will start off with none other than the one and only Tobias talking about local first counterparty discovery. Tobias, take it away.
Thank you very much for the introduction, Chris, and hello everybody here and out there. In short, the story is that there's Alice, Bob, and Charlie, and they want to find out in Anoma, like, how does counter discovery actually work, and how can we do it local first, right? And that's very abstract, so I have a little prop that I will use. So basically, whenever the teddy bear arises here, and then we will have toy examples. And the toy examples here is like, well, obviously, like, it's a toy example, because if I do like a local first auction on this thing, like who wants to have this teddy bear, then you out there are probably out of the question, because somebody might want to have the teddy bear. Again, who wants to have the teddy bear? Oh, right, yeah. He was fast demo over the teddy bear is gone. But yeah, basically the teddy bear is whenever it's a simple explanation of the concept. And here we're going like, yeah, where obviously Bob is closer to Charlie, so if I'm just gonna give this thing away, I want to minimize the cost for shipping, so it goes to Bob, and Charlie unfortunately has the short end on this deal. Right. So this is in very short like what local first counter discovery looks in the toy example. Good. But let's go a little bit more slowly. Moreover, more slowly means also, like, I forgot to say 2 things. I will also touch upon 2 other topics. So like the main topic is really local first counterparty discovery, but there's 2 more things involved. Related to the solving stuff, this morning we will talk about frequent batch auctions, which is one thing that we, I think, need in the DEX business. And then there's one more surprise fact, more in the theory department, that you should look out for whenever I get really excited about math and stuff, right? So, but back to counterparty discovery. What is it actually? So, there's a couple of things around it, like the obvious idea. Well, and the question, like, anybody out there want to bother with me? And it should be fair for all. Like, everybody should be able to participate in the bartering with me. And I want to have this maybe as a peer-to-peer, like as close as possible to the people, so to speak. That's one thing that we want. But really, the core of this talk is then we want to have a variation of this general problem of counterparty discovery to find somebody else to trade with. And the additional thing is I want to minimize the distance of the people with whom I interact first, let's say. And you might say, well, that's a nice toy example, and yeah, I got it, but what does it actually bring to the table? And here we're now talking like money and DeFi and latency. So a side effect of if you're close to each other, that the latency is very close. So here we are even in a real-time local audience environment, but to out there, I mean, if latency in a real-time strategy game is bad, like, you don't play it, right? So, and similarly for the DeFi game, I think what we can bring to the table is a way of thinking about how we could make this thing more interactive to the user. Right, and in short, the local first really brings this idea of that we keep things close to us. And you would say, but wait, but that's just a very simple minimization problem. Like, why are we here to talk about this? I mean, we don't need a research department for this, right? I mean, I can figure this out, right? It's just like video algorithm, just standard textbook. So, what is really going on here? So, and now we're actually switching to rather the DeFi context and the solving business, which is incredibly competitive and has many players that are maybe not quite as honest as you are there. So they might try to fool you and say like, yeah, I'm gonna do something with you, and in the end, last minute say, oh no, sorry, I changed my mind. Right, so even if there's somebody pretending to be a counterparty, you will not know until the very end. By which I mean, like, until the solving has been done and the settlement has been done, which involves a global consensus. And it's just like extremely slow from a UX. If for everything I was to do, I have to wait for the global consensus to finish, like going once across the planet and back, at least once, more like twice. Right, so how do we solve that? And theory department tells you, well, you can't. But there's hope. there's Martin Kleppmann, who has written a nice paper, and he's also a head figure, maybe even of the local first software development. And the idea is they're simple, and in local software it's simple. You just keep the data local to yourself and things get more speed up. But for the purposes of this talk, what I want to highlight is that he has a very interesting view on how we might switch around the exact definition of availability. And here the idea is that we are not interested in availability in pure essence or whatever, but basically we care only about the percentage or the expected latency. And I would even add as observed by the user, right? So what I want is I add some kind of user experience which is much more snappy and quick than, and combine it in a meaningful way with what we also need to do. I mean, we cannot solve problems that are impossible to solve, but we can work on the UX, and I think that's a big factor in the business. So far, so good. All right. Okay. Then I would go explain like roughly what we can do here. So once more, coming back to the problem at hand, it's counterparty discovery. We want to focus on the discovery part, but keep the settlement in the back of my mind. The fairness and peer-to-peer stuff, well, bracket that out. We think just now about the minimization of latency and distance, and I will have, of course, in mind the latency in the application. But for the sake of explanation, we are now again in teddy bear land. We will explain this in the teddy bear land, like in the example level. But the short idea of the algorithm is that we want to have UX such that we get to the user a very quick confirmation of whenever we find a match of somebody that might want to trade with us. That can be very quick, and then afterwards we wait for the confirmation. But we might be very happy to wait because we know there's a good chance it works, right? And the simple algorithm is that for the case of Alice having the teddy bear, now she wants to announce this essentially like, I want to sell for free, and there's Bob and Charlie anyway, B and C that want to have them. And how do we go about the counterparty discovery now? Good. The first abstraction is that we will put data centers essentially spread out all over the globe, and some of these will be closest to you where you submit your intents, right? And then we impose a structure on these data centers such that we pull them locally together. Let's say like per country, we pull all of the validators per country together, and then maybe per continent, and then finally we go over the oceans. Then we have the hemispheres, and finally the global pool of all validators are like represented by the center node. So to give you an idea, so now how does this local first algorithm work? It's, first of all, the intents are known instantly, more or less locally. And if no match is found locally, then we have to go to the next bigger level. So moving up, now we are on the level of countries, and still there are no match found. We move up on the level of continents, and still no match is found. However, then things get interesting in that on the, what is it, like northeast quadrant here, no, northwest quadrant, you have that the Bob's and Charlie's intents actually start matching. And at this point, we can already notify both of them, oh yeah, you have a partner there out there that wants to do trade with you. In this case, very simple, right? And for Charlie, we don't know yet. So then things move up to the next level, Northern Hemisphere, and well, the old found match is still there. Moreover, Charlie will get the information, sorry, this time not you, but keep trying. And finally, we already move up to the global level, and at which then we can move on to the settlement. So that is the very simple structural idea of how we can implement a local first matching strategy, discovery strategy, and then the matching, and then the solving, right? What I haven't now squeezed into this slide is the time dimensions, or some details on like how the time dimension is going to look like. And for that, I just have one slide that's maybe a little bit demanding, but let's just go through it like one step at a time. So you will rediscover the hierarchy of our pools, which have like the local pools at the bottom, and the inner nodes are like more bigger pools, and finally the biggest global pool at the top. And roughly The z-axis is going to be like essentially space, and as we move up, I call it the different levels or the depth, right? And then let's talk about the time dimension. So first, as you remember, I went from outside in. So on the local levels, we can with the low latency, we can have quick rounds of finding matches for your intents. Then at the end of those rounds, maybe we found matches and we are already happy, or whatever is left over, so to speak, and the information of what has been found is moved up to the next bigger level. So now it's not only single pools, but actually already bigger pools know about what is still up for matching, and we get actually more stuff that is meeting each other. And then we just keep going, and sooner or later we'll move up on the global scale, at which we then can, on the one hand, start the actual settlement of the matches that have been found, and on the other hand, we can just keep the stuff that's not matched yet around for longer term plans, right? And yeah, and now we come to the point where I take questions if there are any, or comments, or like clarifications. Or yeah.
Yeah, here, so when you do the local first one with the green with the local data centers, does that start in parallel in all the data centers, or the data center that's closest to ever starts the search?
Right. So for this, in parallel, strictly speaking, doesn't make sense if you think about, because there's no global clock against which you can synchronize. But by and large, the intuition that is more or less like concurrently this is happening.
Yeah.
But now if you take this picture, you can, of course, interleave these things, right? You can have several, like, it's not that, just to keep the picture clear, I show you that I just move up to the next level, but as soon as I'm moving up stuff to the next level, I will keep it locally bringing in, like, listening for new intents, which I'm also working on. So it's not that we keep working constantly on all levels. And the interesting part is that, moreover, it is not, it's basically that's just like everybody's working all the time. It's just like on each machine you will have, so to speak, different levels like on your machine on which you're working at this moment. So there's a constant flow of matching and of new orders. Orders are, however, always submitted at the lowest level in the model I'm doing. So like, and moreover, what I want to say, like this moving up strategy, like that we just move up to the next level, is just a very stupid quick implementation, if you will, just to illustrate the things. You can start thinking about like, well, okay, maybe certain intents, we know that typically they tend to be matched on the other end of the planet, so I'll not go just upstairs, but to the other hemisphere already, right? Yeah, more questions, yes?
So perhaps I missed something. Thank you for this so far. Why are we, can you remind me why we're interested in local first? What if someone on the other end of the planet is willing to pay 10 times as much for what is now my teddy bear? Isn't that economically inefficient? What have I missed, please?
Right. If you have this type of scenario where you really are interested in the very best price, then if you put that in that tent, it turns out that it will not be matchable at the local level, because it talks about the global level, and then there's actually also even no point in putting it locally, right? Yeah, absolutely.
I see. So it's just different use cases. Thank you.
Yeah. So basically, it's also that the idea is that common stuff that's commonly traded it's also like quicker settled. Like that's the whole idea. If you have a very specific thing, and also what you just said, like also in some draft of a blog post coming out soon, I have this actually as a specific case. Like if intents always occur such that, well, somebody wants X and the person that has X is always on the other side, then the whole business is superfluous. Well, because it will always travel to the global pool.
Can you give an example of an asset for which this structure might be useful?
I mean, my example is really swaps. So any swaps of any type, right? So USDC for ETH, whatever. Yeah.
I think if you think about, for example, if we're dealing in, let's just use them as a simple example because the topology is well understood. with fiat currencies, where actually the fiat currencies are not just issued by, it's not just that you have an account with the US Fed, right? The Fed has, or banks have accounts with the Fed. Then they give accounts to customers or give accounts to brokers, which give accounts to customers. So the thing which you're typically transacting with is not exactly a US government debt obligation, right? It's like some banks, proxy for a US government debt obligation, as Julio was talking about. And if different users are a fair amount of the time willing to accept, various kinds of these sort of proxy debt obligations, it might not be a bank, it might be, Chris, I say that I'm willing to owe you €5 if you'll, pay for my lunch or whatever. Maybe this would be an intent in the pool, and that could benefit from this kind of matching, because often you would, if this is a widely distributed asset.
This is something that happens a lot.
Yes, yes.
Thank you.
And thank you for the question, because now I'm remembered that I will later talk actually about there's an important parameter in the experiments that I'm soon going to explain to you, where it's really depending on how much order flow you have. If you have very sparse order flow, this is all not necessary. It assumes that we will be able to actually also, through some of the ideas that we're developing at Anoma, to have more people that actually will bring in new order flow, and also like that's basically, and then also to join all the order flow that's right now fragmented over different solvers, right? So this is actually like preempting that at some point we will at the point where we'll have to deal with a lot of order flow, such that locally the chances that this is happening soon and quick actually are suitable. But I'll come to that in a bit. I will, for those that don't know yet, quickly recap the idea of frequent batch auctions. Unless somebody else wants to do this for me right now. No, okay. Patrick is not here. Patrick would be great to do this. Anyway, so frequent batch auction, it's an idea that goes back to Eric Budish a long time ago, actually, relatively speaking. And this is actually the graphic from his paper. So let's maybe quickly just go over this graphic. So it shows you essentially across the horizontal a line where you have time. And then you have short periods of time, and if you look closely down the stairs, it says to the blink of an eye. So blink of an eye, that's about 100 milliseconds, right? So within 100 milliseconds, it's like, I can't even do that fast. I can't. This is the frequency at which different auctions are going for actually trading at stock exchanges originally. That's the idea. And what's the benefit of that? Well, in that paper, like the main point is that we want to avoid the race for latency. We've heard this morning in the first talk about across, where there's the first in, first out principle. This is a stupid composition for latency, which is just detrimental to the whole. It just doesn't buy you anything in the big picture. There's a couple of few people that benefit, but that's not what we want. Especially in a decentralized setting, we're not ever going to compete with the continuous trading. So that's where the frequent batch auctions may come to the rescue. And so what we do is, at quick intervals, we take a look at the intents, try to match them quickly, and then move on to the next batch. And whatever is not matched can either stay there or maybe times out, right? And my thought was, when I was doing more or less this preliminary research, was this, well, could this just work if I take the frequent batch auctions and put them on this diagram? So wherever you see like one of these oblong, oval cylinders, this is just a frequent batch auction going on a certain level. And then you just interleave them a little bit clever, not even really clever, and let's run some experiments. What do we get out? And what do we expect? Well, maybe there's several factors in there. So first of all, like, if you look closely at this hierarchy adds additional fragmentation in time. In that, well, if I just am too late, I might just miss the counterparty and then have to wait actually longer. And if I look close at my graphs, I can discover that. But let's just get very quickly to the core elements of these experiments. So without too much cherry picking of data, I have just created intents of the following shape. It's 4 tuples, and the first tuple tells you about when the intent is arriving. And time is just between 0 and 1. And free to choose for you what you want for one, like 1 day, an hour, a year, whatever, is the stack. And then at a certain rate, actually a Poisson process of waiting times, new intents will come in. So each intent will come at a certain timestamp, and here in this case I take the simplification of a centralized place essentially where things originate. Then the second component is that what do we want? So I just have numbers for essentially currencies. So the first intent says at time 0.6 something, I want currency number 25. It's not a value, it's just currency number 25. And I'm actually located at this address. So what looks like an address is just a location. And finally, it's the sequence number, just for essentially being sure that I don't mess up in my implementation. So I have the 3 median intents and the final intent. So I have generated, the first step in my experiment is I generate a bunch of intents, essentially at random, equally like each want for a certain coin, if you will, certain asset is like, has the same probability, and the waiting times are Poisson distributed. Right, and then we have 17,578 intents to solve. Right. And at this point I want to thank Robert, who just had a practice presentation, and I have to explain this one, because what do we do here? Right, so you remember this nice tree, right? And it has a certain width, and you count the number of nodes in that tree. So that's 2 to the n minus 1. And basically, I run the same experiment for 1, 2, 3, 4, 5, 6 different settings. Only the global pool, layer 2 layers, 3 layers, 4 layers, 6 layers, 6 layers. So that in the most refined hierarchy, I have 32 pools at the bottom, and I have the hierarchy going up to level 5. No, level depth is downstairs. So this is depth 5, and the top pool has always depth 0. This is important for the next thing. So far, so clear. The interesting thing that you get away from this data is that almost all the intents are always solved. Like it's about 17k and a half, and 17k gets only 500 intents do not get solved. So it's a pretty good ratio of solving. Right. And now comes the scary slide, in which I think I have time to go through this quickly. But I will speed up a little bit. So there's 3 things. The first observation is that for each of the experiments, there's the value created and total. It's simplified. It just tells you, like, for a certain established measure for value created, I get essentially the same value created for each of the settings, if I tweak the parameter over there a little bit. Okay, so the discount factor is pretty low. So tweaking the discount factor, you get to this point where each of the settings creates the same value. So in the expected value of participation in this is good. And what is roughly it means, like, whenever I found a counterparty, I get one unit of value created. But if I have to wait for this long, it's almost going to nothing instantly. And if I look at the graphs, I can see this kind of that basically, like, what I want to tell you actually is that if you look at this third line of each of these experiments, it tells you at which a rough estimate of the percentage of matches at the respective depth. So in the first you have this long line of zeros. That means basically everything is matched at the only pool. That's to be expected. So when we have depth 2, then the global pool, the upper level pool, gets about 20% of the matching done, and everything else actually already goes on the local pool. And the interesting thing is, for me, even down there, where we have the very wide tree with 32 pools at the end, at each level, I have a contribution of matching to the total value created. And well, that was a lot of things I said there, but there's 2 takeaways from me. First of all, I find it, just for a theoretical mathematical result of a quick experiment, very interesting that there is a not even so contrived parameter choice for which I have value created at all levels. So basically, all the frequent batch auctions do something, and moreover, it's a choice for me whether I want to have, like, quicker response time possibly, or I want to keep things a little bit slower. So, and the real interesting thing is that I've sent some research on scale-free phenomena that's lurking there. And that was the thing that I got really excited, and it brings us back to the order flow. So like 1 minute more I take off here, and maybe another slide will go later. We have discussed that if there's more order flow, this thing will work well. If there's not enough order flow, essentially the leaves will dry out and everything will have to wait to go upstairs. And then when I see this, I will just find out, okay, I just have to keep my hierarchy lower, or I have to get more order flow, or make the periods longer. Right. So looking at time, I'm about to finish. I want to say 2 applications. So I have discussed this idea quickly with Dave Oger in Brussels at ETHCC, and he was like, yeah, well, it's a pretty good idea. Well, why don't we do that actually? And he sat down and wrote this up in some of for the case of data availability, and there it works really well because you just have to disseminate data and there's no conflicts. And well, check it out on YouTube. Much more interesting. This whole thing goes back to way back. ETHCC 5 in Paris, and Chris is talking about this, and if you look at this slide, there's private bartering. And now comes the moment in the talk where we just like change gears like just before the conclusion, which is always a hard point. But I find it really interesting and very important because Anoma has this information flow control feature, right? So all the talk, I was talking about minimizing distance and minimizing latency, right? There's like this dimension. And now we go for a completely different dimension. And it's just like how much information I'm gonna go throw out there. Right? And whoever is taking screenshots is gonna be rewarded apparently. So basically we have a different dimension. If you change the metric here, then it's, if I care suddenly about information flow that needs to be minimized, then, okay, well, whatever, laughing is going on here. Then I have this private bartering. I will not divulge more information than necessary before I go to the trade. And at this point, I find it really interesting that that might actually involve several going back rounds. I get a first confirmation. There might be somebody that is vaguely looking in the same direction. Do you want to catch up with them and maybe discuss this? And then over the course of times, you might have several rounds of bartering and haggling maybe even so that you get to the final. Okay, that was the brainstorming part. Now back to the conclusion. I told you I want to tell you about local first counterparty discovery. And I explained to you, basically it's Alice, Charlie and Bob sitting out there and wondering how can we meet each other or find counterparties in a local first manner. The motivation is that in this way, as an aside, we can combine a low latency for at least at the level of the UX with a global reach, exactly, for example, to maximize the value of the counterparty discovery. And then I think I had this idea that, wait, this goes well with the frequent batch auctions, and we might just put those frequent batch auction on a tree and just run them. And that needs more research, of course, but it seems to be a good way to go forward, actually, to address these issues of how we can work against solver centralization. So I want to conclude with the good old words. Think globally, act locally.
Thank you, Tobias, for that lovely exposition on local first counterparty discovery. I think we have time for one question. Any questions from the live studio audience? Rob.
Yeah, but Jamie also had
No, go ahead.
quick comment. I'd like. It would be interesting to see that experiment repeated, where you change it from distance to how much information you leak. I think that would be interesting. And then I think Jamie can ask this question because that was quick. I'll leave that one.
I just wanted to thank you for the lovely talk. I wanted to mention the birthday problem.
Yes.
So it seems to me you commented at some point in the talk that it adds value at every level. And I wondered if this was essentially a manifestation of the birthday problem, that even if...
Yeah, I was exactly scared of these kind of questions. Like, but look, you just look up the book on queuing theory on page 307. Like, it's explained there. Why didn't you read that? So I have an inkling that this phenomenon has been researched in the literature in different guises, especially people that actually know something in more depth about statistics, and probability theory, in particular queuing theory. So I'm very much interested in exploring that direction. Yeah.
The spin I'd put on, I would put on this is I think you're right. I think there probably is something there, and it might be original. Things like it might have been considered, but precisely this might be a novel framing of the problem.
Thank you very much for that great feedback.